Good morning, ladies and gentlemen. Our final portion of our electricity unit is about capacitors in series and parallel. And you'll see it's going to follow most of the same rules as resistors, but there are a few small differences. In our first example over here, we're going to talk about when we place capacitors in parallel. How do we solve for the total capacitance? Well, if you place in capacitors in parallel, you can take a look over here. It's as if especially if the battery is connected over on one side, that each capacitor together will create an additional area for charge to be stored, which means that if I want to find the total capacitance, all I really have to do is just add them up. So when I have capacitors in parallel, my formula will be simply adding them all up. So if I had 3 capacitors, each one equal to 50 picofarads, the total capacitance would equal to 150 picofarads. Now, if I had those 3 capacitors in parallel, just like with resistors that are parallel, how does the voltage drop across each one compare? Well, again, each one is separately connected to the battery. So each one is on its own circuit. So since each one's on its own circuit, that means the voltage across each capacitor is the same as the battery. And because each one is separately connected to the battery, ultimately, when I solve for the total charge, if you think about it, well, with these 2 plates over here that are in parallel with each other, okay, we have a charge stored on one plate, charge stored on the second plate. So overall, the total charge of capacitors placed in parallel, you simply add them all up, okay? So the voltage of the capacitor is the same as the voltage of the battery, and the capacitors we each add up individually. But keeping those rules in mind, okay, let's actually do a quick practice problem. If we take a look at our previous example of the 3 capacitors placed in parallel, each one with 50 picofarads, and let's say they were connected to a 10-volt battery, okay? How do we solve for how much charge is stored on each one and how much voltage is on each one as well? Well, rather than an RVIP chart, okay, we're dealing with capacitance, the charge on the capacitance, the voltage or the potential difference, and instead of power, we're going to deal with the energy that's stored on the capacitor instead. So just like with RVIP charts, when we listed how many capacitors we had, 1, 2, 3, or resistors, we have a total, we follow the same basic rules. 50 picofarads, 50 picofarads, 50 picofarads. Now, the only difference is, rather than using V equals IR or P equals VI, which we use for resistors, we're going to use C equals to Q over V, and UC equals to 1/2 QV to solve for the different portions on the chart. So again, my total voltage is a 10-volt battery. In parallel, capacitors add up to 150 picofarads. So if I want to solve for the total charge, well, that would simply be using this formula over here, Q equals to C times V. Now, pico, of course, means times 10 to the negative 12, but I'm not going to bother converting it. Rather, I'm just going to leave in picofarads. So that way, when I do 10 times 150, I get 1,500 picocoulombs. Okay, so the unit stays in there. This is a parallel circuit, so that means that voltage is the same across each capacitor, which means that each capacitor also has 500 picocoulombs stored within, okay? And notice that all 3 charges, so Q1, Q2, Q3, they all add up to be a total charge that's stored on the capacitor itself. And for energy, in this case over here, I would use 1 UC equals 1/2 Q times V. So I would end up with 2,500 picojoules in each case. And total energy would be 7,500 picojoules. Okay, so it ends up being very similar to an RVIP chart, except now we're dealing with capacitor formulas instead. Now let's take a look at capacitors in series. Okay, meaning we have one capacitor placed after another, placed after another. Now the thing is, when capacitors are placed in series, the total capacitance decreases. And the main reason for that is because we have all these spacing between each of the capacitors. There's more space between capacitors, which means that we end up with a lower capacitance according to the formula C equals to epsilon naught A over D. So if I'm adding more and more capacitors on when it's in series, okay, so in this case over here, as there's a greater air gap, in order to solve for a decrease in capacitance, just like when I was solving for a decrease in resistance with resistors in parallel, capacitors in series are solved for using an inverse. So for 1 over capacitance in series, we would do a summation of all of them over 1. So if I have 3 capacitors that are each 50 picofarads, that would be 1 over 50 plus 1 over 50 plus 1 over 50, which ultimately equals to 3 over 50. So the total capacitance in series would be 50 divided by 3 picofarads. And in this case, when we're talking about what variable stays the same with resistors in series and what variable stays constant with capacitors, well, with series resistors, we knew that current stayed the same through each resistor because there's only one flow of charge going through the circuit. But with capacitors, it's very similar, but we don't have a flow of current anymore. Once capacitors are fully charged, current stops. So instead, what stays the same is charge. Okay? And it doesn't even matter if you have different sized plates. Ultimately, if you have a certain amount of charge on one plate, that's going to repel these positives onto the next plate, which of course will then repel these positive charges into the battery. Of course, I'm talking about conventional currents. Normally it's electrons that are moving, but it's the same idea. So ultimately, when I want to solve for charge, I have to understand that charge on each capacitor is going to be exactly the same. Okay? So in the end, it's as if I just have one regular capacitor with one positive plate over here and one negative plate over here. Okay? So my total capacitance, I will do an inverse to add them up. However, when I'm talking about potential difference, okay, with potential difference, just like with resistors that are placed in series, the total voltage of the battery itself is equal to V1 plus V2 plus V3. Okay, they add up just like in series. So the main point here is that Q is the same everywhere. V is the same. V adds up. The only difference would be the capacitors in series you'd solve by using an inverse. Now let's actually do a quick example question of my 3 capacitors in series. We'll again still start with 10 volts. And we have 3 capacitors, each one with 50 picofarads. We'll create a CQVU chart. 1, 2, 3, and a total. Okay, so the battery is 10 volts. Each one is 50 picofarads. And we're going to solve for the total. Of course, because this is in series, we're going to use inverse. That means the total capacitance in series is 50 divided by 3 picofarads, or the same thing as 16.67 picofarads. So our total is 16.67. In order to solve for the total charge, we would use Q is equal to C times V. So in this case, I'll end up with 166.7 picocoulombs. And I know that charge on one plate is the same charge on every plate. So this is going to be 166.67, 166.67, 166.67. And when I was solving for the potential difference, V is equal to Q divided by C, and we'll see that the 10 volts is split up evenly. So we end up with 3.33 volts at each capacitor, and they all add up back to the original total. The energy stored in a capacitor is equal to 1/2 Q times V. So in this case over here, we end up with 275 picojoules stored on each one, with a total of 825. So this is how you solve for capacitors in series. If you happen to have more than one capacitor in a combined series and parallel, we follow the same rule as before. Let's say this is 100, each one's 100 farads. We have capacitor 1, capacitor 2, capacitor 3, and let's have it connected to a 120 volt source. Okay? So in this case over here, we would start simplifying first. We would simplify capacitor 1 and 2, so therefore it becomes C12, C3, and it becomes a series circuit. 120 volts. C3 is still 100 farads. Whenever I combine capacitors in parallel, I simply add them up. So my C12 is equal to 200 farads. And now I can start making my CQV chart. So when I make my CQV chart, I have 1, 2, 3, 1, 2, my total. I know that my total battery is 120 volts. Each capacitor was 100 farads. And combined, 1 and 2 became 200 farads. Now, how do I find my total capacitance? Well, my total capacitance is, of course, based on a series circuit. So therefore, I would do 1 over capacitance in series equals to 1 over 200 plus 1 over 100, which equals to 66.67 farads. And if I do Q is equal to C times V, I know 120 times 66.67 is equal to approximately 8,000 coulombs. Okay. Now, I have to start working backwards. I know that this over here, 1, 2, and 3 are series. In a series circuit, charge stays the same. So because in a series circuit, charge stays the same, that means my 8,000 coulombs is going to be over here and over there. Okay, which means I can now solve for the voltage. Voltage, of course, is equal to Q divided by C. So 8,000 divided by 100 is 80 volts. 8,000 divided by 200 is 40 volts. And notice the two of them add up back to the original total of 120 volts. The next step, of course, is to realize that, let's use light blue. Okay. The next step to realize is that C12 over here is really a parallel combination of 1 and 2. So whatever information I use over here, I can bring back for my parallel circuit. Now, because this is a parallel circuit, I know that voltage stays the same. So if voltage stays the same in a parallel circuit, that means that this is 40 volts and this is 40 volts. Doing Q equals C times V, I end up with 4,000 coulombs, 4,000 coulombs, and then I can proceed to solve for the total energy stored as well. U is equal to 1/2 QV, so you end up with 80,000 joules, 80,000 joules, and 160,000 joules, meaning that the total energy stored will be 320,000 joules. If the numbers seem abnormally large, well, that's because normally capacitors aren't measured in farads. They're measured in picofarads, nanofarads, and microfarads. Okay, they normally don't hold very much charge.